ऑब्वियसली आ गया है, वहाँ तक एक्चुअली जो इस टेक्नोलॉजी को समझ चुके हैं या अच्छे से कंटेंट बनाना जाने लगे।
Good morning, students. Today we are going to discuss about integral transformation. Integral transformation of a function in a closed interval is defined as a function pp, which is equals to the transformation of a function fx with respect to parameter p, and it is given by integral a to p kx p fx dx. kxp is a function of x and p whose domain is prescribed and known as the kernel of the integral transformations. The various type of integral transformations, which are some special type of integral transformations based upon the kernel of the transformation and the region of integrations, are defined as. The number one and the most important transformation is the Laplace transformation. The Laplace transformation of a function fx denoted by Laplace and fxp, and it is given by integral 0 to infinite e raised to minus px fx dx, where the kernel of the transformation of the Laplace transformation is e raised to minus px. The second transformation is the Mellin transformation. The kernel of the Mellin transformation is x raised to p minus 1, and it is denoted by Mellin transformation of fx with respect to p, and it is given by integral 0 to infinite x raised to p minus 1 fx dx. The another transformation, well-known transformation, are the Fourier transformations. There are three types of Fourier transformation. One is the complex Fourier transformation, which is denoted by f of fxp, and it is given by 1 upon root 2 pi integral minus infinite to infinite e raised to iota px fx dx. The kernel of the complex Fourier transformation is 1 upon root 2 pi e raised to iota px. The another transformation is Fourier sine transformation, which is denoted by fxp, and it is given by root 2 upon pi integral 0 to infinite sine px fx dx. The kernel of the Fourier sine transformation is root 2 upon pi sine px. Similarly, the Fourier cosine transformation is given by, denoted by fc fxp, and it is given by root 2 upon pi integral 0 to infinite cos px fx dx. The kernel of the Fourier cosine transformation is root 2 upon pi cos px. Similarly, the another transformation is Hankel transformation, which is denoted by h nu fx with respect to the parameter p, and it is given by integral 0 to infinite x j nu px fx dx. The kernel of the Hankel transformation is x z nu px. We know that the j nu px is the well-known Bessel function of order nu. First of these transformations, we discuss about the Laplace transformation. The Laplace well-known transformation is, if a function fx be a real or complex valued function defined for the values which are greater than 0, then the Laplace transformation of this function fx, denoted by Laplace transformation of fx with respect to p, or we will take it as fp, is defined as fp is equivalent to Laplace transformation of fx with respect to p. This is equals to, by the definition of the Laplace transformation, this is equals to integral 0 to infinite e raised to minus px fx dx. Now we discuss some properties of the function. First property of the function is sectionally continuous function. Which function is sectionally continuous? A function fx is known as sectionally continuous in a closed interval AB if it is continuous in all the open subintervals of the closed interval AB, and at the endpoints of these subintervals the left hand or the right hand limits exist and finite. So a function is known as sectionally continuous if it is continuous at all the open subintervals of that closed interval, and at the endpoints it is the limit, left hand limit or the right hand limit exist but finite. Another property of the functions is the function of exponential order. What is the exponential order? A function fx is said to be of exponential order gamma, where gamma is a positive number as x tends to infinite. If limit x tends to infinite, e raised to minus gamma x fx, this is equals to a finite quantity. If this is a finite quantity, then the function is said to be a function of exponential order gamma. For example, or in another definition, another way we can define it as that if a given number x0, there exists a real constant m which is greater than 0 such that modulus of e raised to minus gamma x fx is less than m for all x greater than or equals to x0, or we can write it as modulus of x is less than m into e raised to gamma x for all x greater than or equals to x0, then we say that the function fx is of exponential order gamma. For example, if a function fx is equals to x square, then we say that it is of exponential order 3. For this we see that since limit x tends to infinite, x square e raised to minus 3x, if we take this limit x tends to infinite, x square upon e raised to 3x, it comes to be 0, then we say that the function x square is of exponential order 3. Now if we calculate the Laplace transformations of some function, the first of the important function is the Laplace transformation of x raised to n. If we find the Laplace transformation of x raised to n, then this is equals to, by the definition of the Laplace transformation, this is equals to integral 0 to infinite e raised to minus px x raised to n dx. By integrating the right hand side by parts, we get fp is equals to the Laplace transformation is equals to minus x raised to n e raised to minus px upon p limit 0 to infinite plus 1 upon p integral 0 to infinite n x raised to n minus 1 e raised to minus px dx. Or again, calculating the value, this is equals to minus 1 upon p limit x tends to infinite x raised to n upon e raised to px plus n upon p 0 to infinite x raised to n minus 1 e raised to minus px dx. If you calculate the limit, then this limit is as limit x tends to n tends to infinite x raised to n e raised to px is equals to 0, then this comes to be equals to n upon p 0 to infinite e raised to minus px x raised to n minus 1 dx. If we integrate again, then we get, and using this again, we get n into n minus 1 upon p square integral 0 to infinite x raised to n minus 1 e raised to minus px dx. Similarly, proceeding in the same way, we integrate by n times, we get it is equals to n minus 1 n minus 2 up to 1 upon p raised to n integral 0 to infinite e raised to minus px dx. If we integrate e raised to minus px 0 to infinite dx, it is equals to 1 upon p. So we get this is equals to as factorial n upon p raised to n plus 1, which is gamma n plus 1 upon p raised to n plus 1. So the Laplace transformation of x raised to n with respect to the parameter p is equals to factorial n upon p raised to n plus 1, or it comes to be as gamma of n plus 1 upon p raised to n plus 1. So we have started the Laplace transformation of well-known functions. In another class, we will discuss about the various transformation of another function. So thank you very much.